Yes. Welcome, ladies and gentlemen. Our friends in New York who organize the World Science Festival, close friends, they have a category in which they, in a way, vote Isaac Newton. We see further because we stand on the shoulders, roughly speaking, on the shoulders of giants. And the category this year was occupied by John Mather. And I think rightly so, even in a literal way. And we tried, I think, about 7 years to persuade him to come to Heidelberg and to meet you. And especially our little friend, she's the youngest passionate fan of yours. She's 8 and her name is Eve. So I have the great luxury tonight that I don't have to tell you the details and to qualify this important invitation we celebrate tonight. We have a new friend, close friend, who has been giving us a wonderful talk last Friday, Hans-Walter Rix, outstanding scholar, director of one of the Max Planck Institutes up on the hill. And we're very happy to get the news from him. So, welcome.
Yeah, many scientists dream of having one big result in their career, one big accomplishment. And for most of them, this dream remains unfulfilled. I do not know what John dreams about, but it doesn't matter in this context because it is very manifest that his professional life has seen at least two, truly monumental accomplishments. And therefore, it's really a true pleasure to introduce one of our most revered colleagues, John Mather, this evening. So John's career started out as a graduate student in Berkeley just after the cosmic microwave background, the echo of the Big Bang, had become discovered. And I think that was the compass for the first part of his career. When he went to New York, as a postdoc, he set out to think through, initiate, and then eventually carry out a space mission that could turn this from a fascinating curiosity into a powerful tool, the microwave background of understanding our universe. He was one of the people leading the COBE mission, which then almost 20 years later did two things, as the Nobel Prize citation showed. First of all, showed that this radiation truly looked like a so-called black body, perfect thermal radiation, which proved that, yes, it had to be the relic of the Big Bang, and the universe early on was actually beautifully simple. And there are many stories that John probably could tell, because measuring that something looks like a perfect black body, better than anything one has in the lab, is actually a hard thing to do. And the other thing the COBE mission measured is that the universe was simple and elegant, but not completely boring. There were fluctuations, some places hotter, denser than other places, the seeds of everything else that we see now. So that is the mission that characterized John's first part of his career, and for which in 2006 he was awarded the Nobel Prize. Already in 1995, and I read today, allegedly, surprisingly, you got called up and said, do you want to take care of, as mission scientist, of the next big thing after Hubble, which now, I guess at the time was called NGST, the Next Generation Space Telescope. All these missions, when they're still in early phases, get get random acronyms and get only named later. And indeed, he took this on. And as a senior project scientist, in the end, your responsibility is to make sure the thing produces astounding data that can change our view of the universe. And of course, Hubble were big shoes to fill, and he will talk about the successor to the Hubble Space Telescope. But one thing I think is in common, Hubble, while it was happening, while it was being developed, in many ways came so often close to disaster. And once it worked, all that is forgotten. In many ways, there were trials and tribulations also for JWST, technical, financial, and political, that John managed to help see through. And of course, as you'll see, now all is forgotten. And I think what characterizes John's work and made his accomplishments possible is progress in astronomy comes from beautiful machines in many ways. And you need to have a science vision, you need to have the technical competence, and you need to have the attention to details to pull all of this together. But anyway, so between teaching us about the microwave background and bringing JWST to the world, along as he'll tell you with many other people, those are truly monumental things. And so I'm very happy that you come here and tell us about it. Thank you, John.
Well, my goodness, thank you for that lovely introduction. It's hard to imagine living up to all of the things that are said, because, of course, I always will tell you that all of the things that I have done are joint projects with many people. It took 1,500 people to build and launch the Cosmic Background Explorer satellite. It took 20,000 people to build and launch and operate the James-Webb Space Telescope. So I'll tell you something about them and something about why we do them and what we found. So here on the picture you see the great new telescope, the James-Webb Space Telescope. It's got a gigantic hexagonal mirror there. It's made out of 18 smaller hexagons, 6.5 meters across, which is bigger than the rocket. It has to be folded up for launch. It is a joint international project of NASA with the European and Canadian space agencies, and we have had a long and very productive process of working together. Despite all the difficulties of traveling across the ocean and shipping things and regulations about what can be exchanged. Anyway, 20,000 people. And so when I was introduced, you talked about all the things that I have done, but in truth, I do not organize 20,000 people. It's a huge project that requires properly trained managers who have a special skill that's way beyond science. So I am in awe of the people who do that. And I don't have pictures of them to show you, but and sometimes I do. And also, I'm very appreciative of our national funding processes in Europe, Canada, and the United States that have made the resources available. I think we've made them proud because we have found most wonderful things with this equipment. And as was mentioned, most of the great discoveries of astronomy come from these shiny new machines of one sort or another. So there it is, as it will be in space, and I'll tell you more about it. But stepping back in time, why are we doing these things? So this is what I wanted to know about when I was small, although I did not have the words to do this question. Where did we come from? When you're a child, usually they tell you a very simplified version of this, and maybe they point to religious texts and say, well, it is so because it is so. So we know a little bit more now. When I was a child in the 1940s, almost none of this was known. It has all been worked out from observations and theoretical calculations. I'll show you a little bit about them. Where did we come from? And indeed, even the question of who are we is a rather complicated philosophical question. What is our history? Are we alone? Are there other living creatures elsewhere in the universe that are like us in any way? And if there are, how far away might there be? Well, where would we look for them? A really fundamental question for science is
Is life itself a extremely rare event, or is it what I would call a thermodynamic imperative, which would means that it will always occur given a chance? So if the situation is correct, then life could begin. So that's my personal guess, but we don't know. Of course, also people want to know, how far can we go? Can we get out of the solar system? And the answer is, well, not that we know of. Perhaps, but astronomers, we travel at the speed of imagination. We travel as far as we can imagine, as fast as we can imagine, all the way back towards the first moments of the universe. And we'll show you some of those stories. So I say astronomers see everything twice. We take a picture and then we tell you a story. So we've been thinking about these questions for many thousands of years. These are words of the Roman poet from, what does it say, about 100 BC almost. He knew of the atomic theory. He knew that things were possibly made out of tiny invisible particles, that there might be more than one kind, but they didn't really know at the time, that they would stick together and grow up to be big things. And eventually he even mentions the ideas of naming things. So linguistics comes into his philosophy. And then, so there's a great number of things in modern science and philosophy that were included in his thinking. So, of course, how do we know these things? Well, we don't know them all till we measure. So this is my life story, beginning here. This is a research farm in far northwestern New Jersey, about 80 miles northwest of New York City. It's a very rural area that reminds me here of parts of Germany, where it's very hilly, and this was a place to keep animals and do research about how to make more and better milk. So it was a very quiet place for me to be, very isolated. The neighbors are quite far away. The bookmobile, the library, sent a truck around every 2 weeks with books, and I got all the science books that I could get. So that was my beginning as a scientist, but I was not very interested in dairy cows. But the sky was beautiful. You could see the dark sky at night. The stars were bright. Comets came around. Anyway, I wanted to know. So what happens next? Well, in around 1946, Lyman Spitzer, who was a famous astronomer, had just finished up working with the Defense Department, and he wrote a report that said we should build telescopes in outer space, not only to look down, as the Defense Department would want to do, but to look up, to do astronomy, because there were so many things you could do better in outer space. A few years later, he wrote a report that said, and if you could polish an asteroid into the shape of a parabolic mirror, you could detect planets around other stars. He was an extremely visionary person. He didn't say how to do it, but he knew that it might be possible. A few years later, Sir Fred Hoyle is shown there in his little car in Britain. He is the person who's confused the entire world about the meaning of the Big Bang. He named the expanding universe the Big Bang Theory, and although it's now the name of a television comedy, it's also confused everyone, because the Big Bang suggests to people that it's like a firecracker, like a small explosion in a pre-existing space. And it's exactly the opposite of what astronomers see, where we see distant objects receding from us in a presumably infinite universe. So it's confused everyone. So nevertheless, it's made it a very popular subject. So then also in 1946, I appeared. So I'm now 77, so I'm carrying on as fast as I can. So what happened in 1948, these two gentlemen on the right and the left, Ralph Alpher and Robert Herman, were thinking about the expanding universe, which had been known about for some time, and we now knew nuclear physics, unfortunately, or fortunately, and we knew that we could calculate the properties of the primordial material, and they calculated that the early universe must have been very hot, and it should have been filled with heat radiation at a temperature of about 5 degrees Kelvin, 5 degrees above absolute zero, which is pretty close to the actual measured value of 2.7. So 1948, they made this prediction. Nobody went to look, so the radiation was not discovered until 1965. If somebody had known there was a Nobel Prize waiting, maybe they would have tried. But nobody even tried. So in 1954 or so, My parents took me to the museum in New York City, and we saw the planetarium show, and people were going to point the great Palomar telescope at Mars because Mars had canals, people thought. So there's a drawing of Mars with its canals, and you say, how come they're not there? So now we think those canals come from the pattern of veins and arteries in the back of the observer's eye. So too bad they're not there, but people were very confident that not only was Mars covered with canals, but it must be alive. So right now it doesn't seem so. What else happened in 1957? The Sputnik was launched, and suddenly the Soviet Union seemed even more threatening than before, and the United States public realized that they could be bombed from above at a moment's notice. So suddenly the United States public said, we better have more science and more engineering to defend ourselves from the Soviet Union. So schools offered science fairs and science courses, and I was the beneficiary of those because suddenly there were many opportunities. 1957. So in 1958, NASA was formed in response to the Soviet threat. And then in 1962, Jack Kennedy
Why, some say,
spoke.
the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
Well, that was an extraordinary speech. He promised everything to everyone. Not only would we go to the moon, we would do everything else too. And that was hard to do. But at any rate, how did we do the moon part? James Webb was the administrator of NASA at the time. He made the plan and he made it work. And so there is definitely worth recognizing with naming a telescope for him. Not only did he start the moon program, but he started up exploring the solar system and started up space astronomy. So we have a lot to thank him for. And among other things, it was only 7 years after the speech that we actually had people landing on the moon. It's hard to imagine that kind of technical miracle when the computers we had were slide rules and paper. And we had started behind the Soviet Union. When NASA was formed, we had not yet had a successful space launch of any sort. So, very brave, very competent person, and he made it work. And by the way, here's a secret they don't always tell you. In the days before spreadsheets, he doubled the budget in the taxi cab on his way to see the president to ask for money for the Apollo program. So then it was enough, but just barely. Can you imagine the national embarrassment and disaster that it would have been if he did not ask for enough money? So this is one kind of risk management that's very important, and many of us technical people would not have thought of it because we're very optimistic. Of course we can do that. Well, yes, we can, but it may take a lot more money and time than you think, which is not exactly the first or last. When Thomas Jefferson sent off the first scientific expedition to explore the western part of the United States in 1815, they spent much more time, much more money. They came back, many people had been lost. They did not publish the results, and nevertheless, it was very important. First scientific research program of the United States. Anyway, coming back to astronomy, how do we know what we know? We have now the desire to survey the universe. How far away are the stars? So we have two basic methods, the triangulation method. Into triangles, you know one length of a side of a triangle and two of the angles. You now know the whole shape of the triangle. We survey the distance to stars that way. If you can't do that because the angles are too small to measure, then you use the standard candle method. If I promise you that those two objects that I've drawn there are really identical, but one of them looks fainter, we say it's because it's further away, and now we can calculate distances. We have also the desire to know about objects moving toward us and away from us. There's something called the Doppler shift. If an object is coming toward you, the wavelengths that we receive are more compressed because they come to us more often than if the object is going away from us. So nature has given us particular chemical marks for particular wavelengths. So when you look at the sun and spread out the light of the sun into a rainbow very carefully, we see dark bars across the spectrum of the sun. And each of those comes from a particular atom or molecule or ion in the surface of the sun. If we see a similar pattern in a distant object, but the wavelengths are all multiplied by some constant, we say that's because the object is going away from us or coming toward us with a speed which we can calculate. So now we can measure the speeds of things coming and going, and we can measure the distances. So in 1929, we got the first graph that shows the expansion of the universe. So we're coming up onto almost a century that we've known about the expanding universe. What the picture shows is a little dot representing a galaxy. A galaxy, as you know, is more or less 100 billion stars held together by gravity. And on the horizontal axis is how far away he thought they were in astronomers' units. In the vertical axis, how fast they're going away from us. And two big surprises. Well, one is that there's a trend. The farther away they are from us, the faster they're going. And how would you explain that? It's as though they were all started together at one time in one place. And just as this would happen if they were the debris from explosion, although we now interpret it as the whole universe is expanding. Another lovely surprise is 4 of them in the lower left corner are coming toward us. That means there's a great cosmic collision coming in a few billion years. And our galaxy will merge with the Andromeda Nebula, which will be very exciting times for future astronomers. However, we will not be here because our sun will be getting a little bit too bright and too hot for us to like it here. We may have to move to Mars or something. So coming back to my own personal story, Hans Walter mentioned that I've got my degree in Berkeley, working on a measurement of the cosmic microwave background radiation. As it happens, that measurement failed to function properly. The apparatus we built went up on a high-altitude balloon, and it did not work. I got to write a thesis about an instrument that did not work. But I got a job at NASA as a postdoc. I was going to try a new subject. However, about 6 months after I got there, NASA asked for proposals for new satellite missions. This is only 5 years after the moon landing. I said, "Boss, my thesis project failed. We should try it in outer space." So he said, "We will call up our friends and we will write a proposal." And we did. And that became the Cosmic Background Explorer satellite that Hans Walter mentioned in the introduction. So there it is, as we imagine it to have been in outer space. It's been up there since 1989 on November 18th. So in 2 more days, it will be in space for 34 years. And presumably it's no longer functional, but it's still up there. So what does it have in it? It has 3 sets of instruments, 2 of them cooled to the temperature of 1.4 Kelvin to get them cold enough so that they don't interfere with measurements of the cosmic background radiation, and an instrument set that's a little warmer but is capable of measuring temperature differences. So there it is, as we imagine it to be, and it measured the spectrum, as Hans Walter mentioned, to extreme precision, and it also measured the hot and cold spots, which I will show you. So then we received our Nobel Prize a little while later in 2006 because other people measured again, and they said we got it right the first time. The first space mission following us was called the Wilkinson Microwave Anisotropy Probe, and they got a much better measurement. Then it was followed again by the Planck mission, which got even better. And fortunately, we all got the same answer, but improved. So there were no big mistakes made along the way, which is a great relief for those of us who build equipment. So anyway, here is the measurement of the hot and cold spots. So if the entire universe had been completely uniform, with no hot and cold spots in it, we think there would never have been any galaxies and never any stars. We would not exist. So when Stephen Hawking saw this picture, he said it was the most important scientific discovery of the century, if not of all time. So clearly it matters a lot. We wouldn't be here without it. So why is that? We think gravity, acting on the denser regions, was able to stop the expansion of the material and pull it back in. So the universe is expanding as a whole, but now, of course, we need the galaxies not to expand. So we're here because of those spots. Also, of course, we don't know what made those spots. If we ever do, we might have a hint about quantum gravity, which is one of the great mysteries of astronomy and physics. The spots are influenced by cosmic dark matter and dark energy, which astronomers can deduce but cannot see because they really should be called transparent. They completely do not interact with light, which makes them very hard to study, but we're working on it. So here is me showing my spectrum of the cosmic background radiation. As you can see in the curve, all the little measurements fall exactly on the curve. And we got a standing ovation when we showed that one to the astronomers, only a few weeks after the launch of the satellite. There I am getting my diploma from the King of Sweden in 2006. They do know how to throw a party. 10 days of parties and speeches. So how are we going to know what happens next? Well, ideally, you would say, well, I know what the early universes look like. I should be able to tell you what happens next because I'm so smart and I know how to calculate things. But astronomy is not like that. Astronomy is too complex. It's like saying, I know the laws of chemistry, therefore I should be able to predict the existence of mice. And so the answer is no, you can't. You have to go measure. So the Hubble Space Telescope was launched only a few months after the Cosmic Background Explorer. And most of you may remember that it was launched out of focus. When it was fixed, then we suddenly got beautiful pictures of the cosmos, and astronomers said, okay, that's beautiful, and it's still not enough. Please build us another telescope. And another telescope would be capable of finding out the most distant universe by seeing farther out into space and using infrared wavelengths. So they wrote a book and said, please build us this new telescope, and that's when I was called in to please join this new project. And I said, of course, I can't imagine working on anything more important or exciting to do. And so here it is, as we pictured it before we launched it, in a short summary of the people working on it. European, Canadian, and NASA space agencies, with pieces from Europe, in particular the European rocket from the Ariane 5, and two of the instruments, near-infrared spectrograph, and at least half of the mid-infrared instrument came from Europe. So great accomplishment and a great partnership that we had there, and very much to be recommended for the future. It is operated like the Hubble Space Telescope from Baltimore in Maryland. And there it is. I'll show you more about it. And it was initially conceived with a requirement for 5 years of mission life for scientific research, and now we are expecting more like 20. So this is why. This is the launch on Christmas morning of 2021. This is the Ariane rocket carrying up exactly where we wanted it to go. So that means we did not have to spend any extra fuel to keep it in the right place. So we thank every day the people who build rockets and make them work. As you know, when they do this, you say, well, there stands my life work. If something bad happens today, on this minute, and the rocket blows up, it's all over. But we were very fortunate. It almost always works. So where did we send it? We sent it out to the Lagrange point L2. The 5 Lagrange points are places where the combined gravity of the sun and the earth will enable an object to move around the sun once a year. So that means they can stay in the same relative position with us. So the Lagrange point 2 is good for us because we can put up a one-sided umbrella, one-sided protective device to keep the sun off the telescope. And so the telescope can be cold and achieve the low temperatures necessary to observe infrared light. So it's the drawing is not to scale. The distance to the sun is 100 times greater than the distance to the Lagrange point 2. So this is actually, in terms of the solar system, very, very close to Earth. So now I want to show you my scary movie. This is like the 7 minutes of terror that they had when they landed the Mars probes, except the difference is this takes 2 weeks, and we can send commands in case if anything is not right. So it's extremely complicated, as you can see, and you can say, well, how did you know that it would work? Well, we unfolded it 4 times on the ground to make sure. And whenever there was something wrong, we fixed it. We had many people come to look at the plans to say, well, we don't think that's right, or we don't think that's right. We have 2 of everything where it's possible. So every motor has 2 sets of electric windings and 2 electrical controllers. So we do what we can to make something so complicated reliable. If you did not, you're taking chances. So we knew we had to do it that way. Otherwise, many billions of dollars, many billions of euros would be at risk. So it worked in the end. All of the possible ways that it could have failed all functioned perfectly. We did not have to use any of the backup plans. So there it is. At this point, it's been unfolded, but it's not ready for use. Telescope is still warm. It will cool down over the course of months. It is not yet in focus, and getting all that to work was a huge accomplishment as well for the engineering teams. So how do you focus a telescope like that? Well, you have to say, find a star, make sure the image of the star is sharp and clear and bright, and then adjust all the mirrors so that it is. All those 18 mirrors have their own motors on them. So now let's talk about what kind of astronomy to do. Well, we're going to observe infrared light. And why would we do that? Because, number one, you can't do it from the ground, and you can't do it with the Hubble Space Telescope. This is a completely new territory of possibilities. Number two, really, there's new science to be done, new discoveries to be made. So here is a picture illustrating a star which is being born inside a cloud of dust. And you can barely see that it's in there because there's so much dust around it. And you might say, well, I thought space was empty. Well, space is not really empty. It is filled with gas like hydrogen and helium, filled with dust grains, which are produced by old stars when they explode or disintegrate after they've used up all their fuel. So there's a star in there and you can hardly see it. But if you use the infrared capability, even the one that we have on the Hubble telescope, there it is, you can see the star now. So why does this work? It's because long wavelengths of light, infrared, can go through around dust grains instead of bouncing off them. So there it is, and it tells you that this is what you need to make progress on understanding how stars are formed, because stars are born inside those dusty clouds. So what else? We want to see things that are too cool to emit visible light. So here's a picture of something we call a planetary nebula, and it's beautiful to look at, but it also tells us there are things there that could not see without. So now if you enlarge the picture, you see and not only is this a planetary nebula, which is produced by a disintegrating star, but there's more than one star there in the middle, and now we think there are really 5. And that's the reason for the strange shape. So there it is, looking at things that are too cool to emit visible light. The third reason is we want to look at the expanding universe. As mentioned earlier, distant objects are going away from us. We receive light from things that appear to be red-shifted. All the wavelengths come to us at longer wavelengths than they started out. So build a telescope that can pick up the infrared to see the most distant universe. So that's the 3 main reasons to build a telescope that we built. So what did we see? Well, here is the first data set that we released. President Biden showed this to the public on July 11th last year, and it's astronomers' favorite picture for a while. So what we see in the middle is obviously a bright star with a hexagonal spike sticking out. that's sort of not very interesting to astronomers because we have a lot of them already to know. But more important is in the middle there is a collection of very bright fuzzy objects which are called galaxies. They are so big and so bright that they have enough mass to bend light. Einstein told us that gravity works by bending space and space-time. So that means when light goes near those big bright galaxies, it can be focused and bent. And that's what we're seeing around a big galaxy. We see all these funny-looking little pink arcs, distorted images of even more distant galaxies. So this is a way to see the most distant objects in great detail. So astronomers were thrilled with this, and we still are thrilled because we are making some progress to answer the biggest question that we were asking, what was the first thing that happened after the Big Bang? How did the first objects grow? So here's one way we do it. We find objects that have curious colors, and they say, well, that object could be very far away. We spread the light out into its own spectrum, a rainbow, and we confirm the story. We look at the shapes, and we say, is that a galaxy? Is it really as we say? And so now we tell the story. So the surprise here was the galaxies that we found are much too bright compared with what we were expecting. Now astronomers are busy arguing about whether this is something very deep and fundamental or it's just we didn't understand. And as usually, you think, we just didn't understand, but we're still arguing about what does it mean. This is the sort of secret of astronomy. Things are never what they seem to be at first. Yes. That's not me. That's not me. Somebody else is over there, I think. So anyway, what this picture is showing is a magnified image of a very distant galaxy. You can see that it has little bright clumps in it, which we call globular clusters. And they're a possibility for what are the first objects that grew from the Big Bang. Globular clusters have maybe 100,000 stars in them instead of 100 billion. So we're learning about how do the galaxies grow. We took a picture of the most distant black hole quite recently. How can you tell if something's a black hole? Well, you see a little thing that's too bright and too compact to be an ordinary star. If you can see it with X-rays, as we have an X-ray telescope in space called Chandra, then we see it very bright because material is compressed and heated to enormous temperatures. So you've seen a very, very, very distant black hole. So this is one of our fundamental questions also. How did the galaxies make black holes, or did the black holes make galaxies? The Hubble telescope told us that almost every galaxy has a gigantic black hole in the center with millions or billions of times the mass of the sun. And how did that happen? We really do not know yet. No. So here is a pretty picture I like to show. This is called Stephan's Quintet. It has 5 galaxies. The 4 on the right hand are about to merge together in the next few 100 million years. They will combine into a single large galaxy. And the top one has a black hole in the center. We can see it as a very bright point object. The 2 in the middle, you can see, have 2 bright eyes there that are looking out at you. There are areas where the gases between the galaxies are being excited to form new stars. That's the pink areas. So new stars being born there. So another beautiful picture I like to show is this one. This is called the Cartwheel Galaxy because of its appearance. The interpretation is that the small galaxy in the upper left corner went straight through the middle of the large one and caused a splash. So the ring of bright material around the big galaxy is a splash of gaseous material that came out from the center and has been caused to form new stars. This is now a kind of star formation laboratory. If you can understand what made those stars grow out there, then you'll begin to understand how stars are born. So here's another one we love to show. This is a galaxy that has holes in it. So you say, how can a galaxy have holes in it? Like a sponge. In a sponge, holes are made by gas pressure as you make the sponge from material. And here we have gas pressure as well. It comes from other bright stars that have produced so much energy they can push the neighboring gaseous material away and form a new generation of stars born around the empty hole. So that's that one. And by the way, this image has been reprocessed by a Judy Schmidt, who's not an astronomer, but she loves to process images and make them more beautiful for us to understand. So you can do this from home. You could do it too. So here is one of our favorite pictures also. This is called the Pillars of Creation. This is a place where stars are being born inside a cloud. And it is clearly been shaped by wind. You can see that there's a wind blowing from the far upper right-hand corner down towards the lower left. The cloud is cold inside. The dust enables the gas to cool off, and stars are born inside the cold clouds. So you say, well, why are cold clouds places for stars to be born? Because the lower the pressure of the gas, the more ability the gravity has to overcome the force of gas and pull it in, make it collapse into a star. So cold places where stars are born are now inside these dust clouds, and the Webb telescope can see inside with its infrared capability. So you see many hundreds of new stars are in there. So anyway, when we understand that one, we'll have made a great progress in understanding the formation of stars. Here's one that I find very exciting because this is a single star. We can see it edge on right in. I don't think I can move my pointer, but maybe. No, I can't move my pointer to be in front of it. But right in the center, there seems to be a horizontal gray, dark bar across it looks like a hamburger in the middle of a hamburger bun. So right in the very, very center of that is a new star. The opaque region around it is a disk of material orbiting around the new star, and it is probably forming planets. So if we were to come back in 100,000 years, maybe the dust would be gone and we'd be able to actually see the planets. So you can see also the star is sending out material up and down, coming out from the new star. This is a very sort of general, common observation of new stars being born. Again, too soon to say we understand, but a very wonderful amount of data to analyze and to interpret. So something else we saw recently, discovery of what's called jumbos, Jupiter mass binary objects. So ordinarily we think a planet like Jupiter is formed in orbit around a new star, but what we found is pairs of Jupiters orbiting around each other. Nobody quite understood this one. It certainly was not expected, but we see them directly in the image of the Orion Nebula, and there are a great many of them. So the Orion Nebula, by the way, is the central object in the sword of Orion in the constellation. And here we see 5 different binary objects have been found quite close together in that beautiful cloud. So, as I say, we cannot predict what we're going to see very well, but we are delighted to have surprises, and then we'll be able to tell you much more later about how did that happen. So I mentioned earlier, everybody wants to know, where did we come from, and are there other planets like ours? So this is the strongest method we have for the Webb telescope. We wait for a planet to go in front of its star. And when a planet goes in front of the star, some of the starlight would go through the atmosphere of the planet if there is one. So now that means that the planet will appear to have a different size according to what wavelength we're using. We can then interpret this to say what is the chemical composition of a planet. So far, the answer is the planets, the small planets, the Earth-sized planets that we've been able to look at, do not have atmospheres that we can see, but the big ones all do. So we can begin to do chemistry of planets in other solar systems. So they're a little bit like Jupiter and Saturn and Uranus and Neptune, but different. And a curious result of all of this is there are not yet known to be any solar systems that are just like ours with a collection of 4 small planets, small rocky planets in the middle, and then 4 large cold planets, gaseous planets farther out. So if you want to know about those, better study our own solar system. So here's our Jupiter. Jupiter as never seen before. So there's the great red spot. It's not red when you use infrared light. This is a point to tell you what makes colors. So, of course, if you're observing infrared light, which the human being cannot perceive at all, what we usually do is we say, okay, the shortest wavelengths will be blue, middle wavelengths will be yellow or green, and longest wavelengths will be red. And so we choose the colors to have some meaning and also significance for astronomers. So now you see tremendous textures in the atmosphere of Jupiter, and we see the great red spot is there. It's been going for ever since Galileo saw it in 1609 or so. And there's tremendous texture. This is a very complicated weather pattern. So very different at the equator and at the poles. By the way, those orange glowing areas at the north and south poles are auroras. Now, the northern lights that we call them, they have them in the north and the south on Jupiter. We have even attacked an asteroid. We wanted to know what happens if you hit it with a piece of metal. And so all the telescopes here on Earth and in space that we could point at that object were deployed at the same time. And you say the Hubble picture on the left and the Webb picture on the right are different. We see the debris flying out from the collision in both of them. And by the way, now we can use this information to help us protect the Earth from killer asteroids. So I guess everybody knows there was one about 65 million years ago that wiped out the dinosaurs and enabled our particular mammalian ancestors to survive. And so people are working on the details of that, but this is part of the necessary information we have to get to be able to protect planet Earth from asteroids. Here's another thing we're looking at. This is Titan. Titan is a satellite of Saturn. It is fascinating for us as it's the only place in the solar system that has lakes and rivers and rain and clouds that are like Earth in any way, but it's very cold. It is so cold that the lakes, rivers, and clouds are made of ethane and methane, hydrocarbons. And so, well, we have to go look. So we have already landed a probe over there. It was called the Huygens probe, a part of the Cassini mission, and about 50 years ago, I think. Anyway, we're going again, and we are sending a new probe, which will be specially to explore this small object. It has enough atmosphere that can support a helicopter. This is a little electric quadcopter that will be landing there in 2034. So we're so thrilled to be able to send it out there, and we'll be looking around to see what is the surface like in more than one place. And obviously we're very curious to know if there are any signs that such a strange environment could harbor signs of life. Are there complex organic materials there, or any other hints that something is strange and different? So it's too soon to be able to get a sample home from there. That's much, much too hard, but we can send a laboratory out there. So far, a relatively elementary laboratory, but still a laboratory. We have taken pictures of Neptune. Here is Neptune with its many satellites with Greek names. And it's a very bright one up there, Triton at the top. And you see Neptune has rings around it like Saturn and like Jupiter. And even the last one in the solar system, Uranus, has beautiful, beautiful rings. And you say, this one is really different from the others because we're looking down head on to the rings. How is this possible? It is because this is the only planet in the solar system where the spin axis is not perpendicular to the orbit plane. So we're able to look right in on the rings. It's very complicated, and the gravitational details are fascinating. The rings are probably organized by the presence of individual satellites out there that you cannot see, but Anyway, a fascinating laboratory for the formation of the solar system if we can understand all of these bits. So I think I could wrap up around now and begin to take questions, but there are many, many places online where you can find more information about the Webb telescope and our scientific results. And if we have more time, I could tell you about new missions that are coming next. So why don't we stop here and have some questions and then deal with that possibility. Thank you. So how do we do questions?
Are there any questions? Yes.
Hello, Mr. Messer. My name is Ralf Lochnin. I have asked about Big Bang. So make some assumptions. Big Bang was a bit earlier than Planck time. At this time it was a singularity, and the laws of nature come a little bit later in the universe, and there's an intrinsic characteristic of space which cannot be shielded and is everywhere and is ensured and starts the expansion of the universe. Heisenberg's uncertainty principles. If I say singularity is a reason, is another reason that we can say Heisenberg isn't the reason for to expand the universe.
Yeah, okay, that's many people have been talking about this question. By the way, I should point out that a singularity does not mean the universe was compressed into a point. Singularity is the neighborhood of an extreme location in space-time. So the early universe is actually a point of unlimited density and temperature as far as we know from the laws of nature. And as you're saying, there may be other laws of nature that apply in those very earliest moments, which we do not know yet. So it's a wonderfully complex, challenging project. And perhaps if we ever do know that, somebody will get a Nobel Prize for that one.
No questions? Yes.
I know that this isn't really related to the telescope, but do you know what happened before the Big Bang?
This is like the other question. Do I know what happened before the Big Bang? And the answer, no, I do not know. There are two big ideas. One is that the conditions that came early on were just special, and we don't really even know what they would be. But perhaps when the conditions are so extreme that even time doesn't mean anything, then before the Big Bang doesn't mean anything either. So that's very speculative, and we honestly don't know. The other category says, well, maybe the universe is bouncing, that it was large before, then it collapsed and came back to a very, very dense condition, and then bounced and came out again. So we can't tell yet. In either case, we need to know laws of nature that we do not know yet. So there's a lot to be found out. We know quantum gravity ought to apply, or many people think that quantum mechanics ought to apply to space and time, as well as to particles. Then what do we do? It's very complicated to think about it. So maybe you'll have a chance to find out.
Okay. Okay, so my question is, what are the systematics to find, well, black holes in general, but also black holes which are really small? Like, what is the systematic to find them? Because, like, really small black holes are really interesting because they, like, could say if they're from the beginning of the universe or if black holes were created after.
I think we don't really know that answer. We certainly are looking to find out that answer. The observations we would need, really small black holes could be observed if there were enough of them. When one went in front of a star, you'd say, oh, it bends the light and we see something. So far, we have not been able to detect any small black holes that way. Then you have to think about how could black holes be made. We have ideas that stars could not collapse directly into black holes. We have actually been watching enough stars now that at least 5 of them have disappeared while we were watching. So how can a star disappear? Well, if the entire star collapses into a black hole, then maybe that could be. We see a lot more cases where a star explodes, and there's predicted there could be or must be a black hole that remains, as well as the debris coming out. Then the big question of how do we get a giant black hole in the middle of a galaxy is a very hard one, and challenge is how do you explain how they could form? So honestly, we don't know, and it's one of the top research questions of today.
Okay.
Thank you so much for this amazing presentation. My question is basically, since you've been involved in many of the telescopes that hopefully give us many more interesting images and questions for the next 20 years, what do you think the next generation of telescopes after Webb will look like, since now we've used infrared to look further than before? What's like the next generation after Webb?
My goodness. Well, I guess you know the Euclid mission was just launched in July, and they're looking for evidence of the dark matter and the dark energy by surveying millions and millions of galaxies. The U.S. is launching one called Nancy Grace Roman Space Telescope. It's named after the first astronomer, head astronomer at NASA, and that'd be looking for that as well. Astronomers have declared that their next priority for the big telescope will be at least as big as the Webb and capable of seeing little Earth-like planets orbiting around stars like the Sun. So this is an extremely difficult optical job to do because the Sun is 10 billion times as bright as the Earth. So this is a huge problem to be able to detect an Earth orbiting so close to a bright star. So that's what they said they wanted. So we're going to try. And so it'd probably take about 20 years at least before we are able to launch it. But it's a definitely worthwhile challenge. So it would not be an infrared telescope, it would be a visible and ultraviolet telescope. That's what the science tells us to build.
John, can I ask you about the lifetime of JWST? You said it should be 20 years. Should we anticipate a sudden death or a slow decay of capability?
Okay. Well, we're hoping for no slow decay of capability. There are a few things that could wear out. Many people have heard that we are hit by micrometeoroids, tiny dust grains that are orbiting the Sun, and we get about 1 or 2 a month. Only one of them in all this time has made a noticeable bump on the mirror. So we're feeling very lucky about that. So it should not wear out because of that. The abrupt end will occur when we run out of fuel. We need rocket fuel to keep in the right place in the orbit and to deal with the force of the Sun pushing on the telescope, which tends to make it turn over in space. So that's called a solar torque. So we have to push back once in a while with rocket jets. So when we run out of fuel, it's done.
Yes.
I have a technical question. As far as I know, there is a technical possibility to connect on Earth telescopes together and increase the effective size of the mirror in this way. So you can connect maybe 4 or 5 2 or 3 meters telescopes and have basically an 8-meter telescope. Wouldn't it be possible to do something similar in space? Let's say something like, not on the scale of Starlink with thousands of small telescopes, but maybe a dozen or 2, and do it so for less money, more bang.
Good question. So yes, clearly it's possible. Maybe I should say it's not impossible. All of these projects are very, very difficult. So if you can do something on the ground, you will always do it first on the ground. Yes, if the objective is to get the sharpest image possible, then the bigger the telescope, the better. If you just want to get the brightest image possible, then a more compact telescope, a round one, is usually better. So I tried quite hard to persuade my fellow scientists on the Webb telescope that they should want a different shape instead of a round telescope. They did not like it.
I was just wondering, what advantage does the Euclid or Euclid, whatever you pronounce it, telescope have over the Webb telescope, or is it just a different way of producing the images?
It's actually some telescopes are built to survey a large amount of sky. So if you have a wide-angle lens on your camera, you can take a large piece of sky at once. The Nancy Grace Roman telescope can get 100 times as much sky at one time as the Hubble telescope. And similarly for the Euclid mission, they get a lot of sky at once. So sometimes that's the thing you really need to make a new discovery.
You show the again. You saw the picture of M74, and there's a bubble in the center of this galaxy. Is there a black hole? Is it a surprise that the black hole is a bubble around?
Actually, I think I know the picture you're thinking about. Yes, one. Yeah, that little blue spot in the middle. That is because the stars in the center are so bright that they push the dust grains away. And so it's had an almost direct view of the center of the galaxy. So that's something we can see better in the infrared than we could see at shorter wavelengths. And almost surely there's a black hole in the middle as well, because they all have them.
Yeah. Thanks, Jakob. Hello, John. I have a question about the dark material and the dark energy. I think it is last week, the Rick tell us the story about the dark material and the dark energy. And the last year, the director of ESA, and he is this place, he tell a story or ideas. He said maybe the Big Bang exploded, but some of the material is not yet exploded. It exists in the space. That's the dark material. So what do you think about this idea?
So are you thinking about black holes that are not yet released or something of the sort? So I'm not very familiar with this question before.
No. I think it is, his idea is the so-called dark materials, because we cannot see, we cannot measure. He said it's from the Big Bang time, the stuff exists, but is not yet exploded. So exists. Yeah.
Yeah. Okay. So as far as we know, the dark matter does nothing except interact gravitationally. So maybe that's incorrect, but whatever we have now, we probably had in the very earliest moments. So similarly, dark energy, although the dark energy only has been important in the last 5 billion years. So another question is, could you ever find out? So nobody has yet succeeded in making a laboratory measurement of dark energy or dark matter. And it's not because we didn't try. People have been spending many, many years building laboratory apparatus to see a dark matter particle hitting an ordinary particle in something, and nothing ever turns up. So perhaps nature has decided not to give us anything to measure. It may be a perpetual mystery. Maybe we should be okay with that. Yeah.
Yes, thank you very much for this great talk. I have a question more of technical nature regarding the thrusters firing to position the telescope and the spectroscopy you do on these planets. Is it a problem that you poison your environment with the exhaust fumes, or is this a non-problem at all?
Are you thinking about exhaust from the jets on the telescope?
Yes.
Yeah. No, they're it's very unusual to fire them at all. Every few weeks, we fire them for a few moments, so they're not a problem. But anyway, good question.
Thank you very much.
Hello, I'm again. I have a question about a black hole. Everyone says the gravity makes us the information is lost in the black hole. and I saw the work of Mr. Penrose. There's a chart, and I see a video from Ms. Silke Britzens. She said the singularity is in the future in the black hole. And we don't consent anything in the past. And if in the black hole there's something on the way to the future out of the horizon, event horizon from a black hole is a past. And so the information is only time shifted. Is it a good or a silly idea?
Well, I don't know.
Okay.
But it's clear that there's a remarkable connection between information and the size of a black hole. So I was completely amazed when this was proven. So, and there are many different interpretations. So ask again in 5 or 10 or 20 or 50 or 100 years. Maybe we'll know in a century. But it's very much a theoretical question. We cannot actually measure those things.
Yeah, so I have another question. I would like to know, how disturbing are your findings on early galaxy formation?
Well, I told you that we didn't really have a proper explanation. We were completely surprised. In the last months, people said, well, we should not be surprised. There are explanations about how stars are formed in the early universe. The temperatures and densities of the primordial material are very different when the universe is young. When the redshift is, say, 10, then the densities everywhere are about 1,000 times greater than they are now. Temperatures are about 10 times as high almost everywhere. So things should be different. And so maybe stars form much more quickly. Maybe stars are much larger when they are formed at first. So the connection between brightness and, which is what we can see, and the interpretation of what is it is pretty tricky when you've never seen one before. So I think in the end we'll say, well, it's just a big surprise, but it's nothing new. It's not a new force of nature. It's very complicated. Yes.
Yes. Hi. Thank you for the talk. I was wondering if so far you've been able to use the telescope to disprove some theories, or you're hoping to use the measurements to adjudicate between theories, or what are you hoping to get as what is the theoretical gain from the new measurements?
Oh my goodness, so it's a good question.
Well, you can choose what you prefer.
So we do have currently a big problem in astronomy because we have two different ways to measure the rate of expansion. So one is based on galaxies nearby, and we see how far away they are and how fast they're going. And we have different ways to measure that. And then we have another approach that starts with the hot and cold spots in the microwave map and have a theory for how that connects to the expansion rate. And the answers are different. And well, for a while we thought, well, that's just interesting. And now it's getting harder and harder to deal with it. So we hope that the Webb telescope data will answer the question. So it's not exactly a theory, it's a puzzle at the moment. So people say a theory is more like a giant overarching concept. And so there's a possibility that some new force of nature to be discovered by working on that question. Because maybe there are no mistakes made yet, and maybe there's just something we did not know about at all. And that would be a lovely surprise.
Well, John, thank you very much. I think your talk was standing on shoulders of giants, it's sometimes breathtaking. And they need to digest to continuous questions. But thank you all for coming. And thank you for this incredible lecture. Thank you.
And thank you for the invitation.